Welcome to lecture 18 of Financial Econometrics, and in this video we are going to cover the concept of multicollinearity. So moving towards the contents, first we are going to discuss what multicollinearity is, and from our basic understanding the lecture of assumptions of classical linear regression model or assumptions of regression. Probably it was lecture 9 or 10. In that lecture, we discussed the assumptions of regression of CLRM, and we are further going to in-depth study those assumptions. So one of the assumptions was a multicollinearity. So if you haven't watched that lecture, I would recommend that you go back and first get the basic idea, because we are not going to cover that idea here. We are going to delve deeper into this concept. Then we are going to see if there is the issue of multicollinearity, then what issues can we face with our analysis. How do we detect multicollinearity? How do we find out that whether our model is having the issue of multicollinearity or not? And then we are going to see how do we solve if there is an issue of multicollinearity. So first, what is multicollinearity? And for that, we are going to see this example where the teacher's salary is the function of years of experience and age. So what we are hypothesizing here is that teacher's salary would increase as his experience increases and would increase as his age increases. Now, the basic definition of multicollinearity was that we saw in previous video was that when two independent variables, two explanatory variables are correlated with one another, then we see that say that there is an issue of multicollinearity. So multicollinearity occurs when the x variables, when we say x variable, we mean independent variables, are related themselves. So in this case, if you see, do you think the years of experience and age would be related? They are, because as the age would increase, the years of experience would also increase, and we cannot increase the year of experience without increasing age. So they are related, right? To what degree, that is another question. But they are related. This relationship doesn't simply mean that there is an issue of multicollinearity, because we say multicollinearity is the issue of degree rather than of being. So what this means is that there would always be some kind of correlation between the explanatory variable, that is a normal situation, but the issue arises when the correlation between those independent variables is quite high. So when we say that the correlation is the issue of degree, then we mean is that if the correlation is higher, then we might have a problem. If the correlation between independent variable is higher, then we might see a problem. And there is an intuition behind it. And the intuition is, if you understand this intuition, then you would probably understand why multicollinearity is the assumption of CLRM. So, what is the reason of this regression? What do we want to do with this regression? We want to find whether the experience would increase the salary. So when we say that, let's say the beta comes out to be, we run the regression and the beta is, let's say, 2. This means for every 1 year increase in experience, the salary would increase by, say, $2, right? or say the beta is 200, so $200. But when we interpret this 200, we say keeping other things constant. So that means we keep all the other independent variables, irrespective of how many independent variables are there in this model, we keep all those independent variables constant, and we interpret this beta. But in case of when there is a high correlation, then you cannot say that an increase of 1 year of experience would increase the salary by $200, keeping the age constant, because we cannot keep the age constant and keep on increasing the years of experience. So you get an idea that when they are related, we cannot, our interpretation starting to fall out. So let's explain this with the help of this Venn diagram. You see, over here we have a dependent variable and two independent variables. Now you see that this part is the part of the y variable that is explained by x2. This part is the part of y variation that is explained, variation is y that is explained by x3. Let's move towards the second diagram. We know what this is. This is the variation in y explained by x2, and this is the variation in y explained by x3. What about this gray area? This gray area is the variation in y that is explained both by x2 and x3. So they both explain it. So that means this part of the information is also represented by x3 and x2. And if we keep on moving, so we say that there is low collinearity, multicollinearity, and as the part, this gray area increases, that means the area, the variation in y that is explained both by x2 and x3, we say that the collinearity is increasing. So this part is the information that is presented both by x2 and x3. So this is the common information. So if let's say this is the situation, let's say this is our y, and say we draw this circle and then we draw this circle. Now you would see this is, let's say, x2 and this is x3. Now you would see this part is the part of variation in y that is explained both by x2 and x3, and none of them presents any additional information. So if we only keep x3, that would be sufficient, or if we keep x2, then again that would be sufficient. So for example, there is this x2 variable and x3 variable. Now, how this x3 is constructed, you can see that it is constructed by multiplying, how this x2 is constructed, this is constructed by multiplying 10 into 2, each value into, into 5. So we get 50, 15 multiplied by 5, we get 75, and so on and so forth. So then that means that this x3 variable is generated from x2 variable. So they both would be collinear. They would move in the same direction with same magnitude. Similarly, x3 is constructed by so this x3 variable is constructed by adding some random numbers to this x3 variable. x3 static variable is constructed by adding some random numbers to x3 variable. Now there is no correlation between x3 and x3 static. So these two are highly correlated, and these two might have some kind of correlation, but they are not highly correlated. So what are the sources of multicollinearity? The first source is that the data collection method employed might have some limitations. For example, if we are collecting samples over a limited range, then we might get a limited range of values, and that might cause multicollinearity. The second reason that might cause multicollinearity is the constraint in the model. So let's say if we have a model where we are going to see the effect of income and the house size on consumption of a family. So now you would see that these two variables, independent variables, the income and the house size, from our understanding, we know that the people with higher income levels would probably have higher house size, so they might probably be related. So this is the constraint in the model that is causing multicollinearity. If we had not incorporated these two variables, instead of say a house size, we have incorporated some other variables, then that multicollinearity would have not occurred. So this multicollinearity in some cases might be due to constraint in the model. The next reason might be overdetermined model, and by overdetermined model we mean that when there are more explanatory variables, sometimes the explanatory variables are greater than number of observations. So in that case we would not have much variation. So normally one of the argument is that multicollinearity by itself is nothing but it occurs due to the smaller sample size. So when there is a higher number of explanatory variables, independent variables in the model, but the observations are less, then we might also see multicollinearity in the data. And the last factor that we are going to discuss, the last source of multicollinearity, is the trend in the time series variable. So let's say if we are going to study the effect of say KC index, KC 100 index, we want to see the effect of GDP and let's say GNP on Karachi Stock Exchange Index. So these variables are time series variables, and when the GDP would increase, the GNP would also increase. That is because of the common trend that they are following. When GDP increases, GNP also increases. So these two might be related, not because of overdetermined model, not because there is a constraint in the model, not because the data method, collection method employed have an issue, but because these two time series variables have a common trend, and when they would have a common trend, then when this would increase, this would also increase. So there would be a higher correlation between these two variables. So let's move towards the consequences. If there is multicollinearity, then what would happen? The first issue that we would see is larger standard errors, and another classical symptom of multicollinearity is that the R square of the F statistics would be higher. Mainly the R square would be higher, but the individual coefficient would not be significant. So for example, in this case, you can see that we have these two independent variables. Their coefficients are insignificant. They are lesser than 1.98 to be significant at 5%. This one is also lesser than 1.98 to be significant at 5%. But we see that R square is higher, it is 0.81. And what does this 0.81 means? It means that 81% of the variation in the dependent variable is due to the independent variables that we have incorporated in the model. But we can see that the individual coefficients of these independent variables are insignificant, statistically insignificant. And when we say statistically insignificant, then statistically we cannot conclude that there is a relationship. These independent variables are affecting the dependent variables. But the R square is saying that there is 81% of the variation in Y being explained by these X variables. So the classical two signs of multicollinearity is the largest standard errors, and you would see that the R square would be high or the F statistic would be significant, but the individual coefficient would be insignificant. One more reason one more symptom can be that if we only change one variable in the model, say if we drop one variable or add any additional control variable, then you would see a major change in the results. So a variable that was having a positive sign might turn into negative, or a variable being highly significant might turn into an insignificant variable. So there would be higher changes in the coefficients, their standard errors, their t-values, with just adding or removing one explanatory variables. And also, if we change a single or few values of a one independent variable, then the estimators might change by a higher degree. So the estimators are sensitive to change in the data. And lastly, the signs of the coefficient may be opposite to what the theory is stating. So whenever we see this kind of an issue, when the signs are opposite to what the theory is stating, then we must always try to find out the reason. We must always apply some diagnostic test. Okay, so how do we detect multicollinearity? First is the correlation. So we have seen what correlation is. We have also discussed in our previous videos how do we measure correlation in statistical package data. So when correlation is higher, say it is 0.9, whether it is negative or positive, so that would suggest that there is a higher correlation between the independent variable. I am just suggesting the correlation between the independent variable. Let's just say there is an independent variable x1 and x2. If the correlation between these two turns out to be, say, 0.9, then the correlation is higher. It doesn't mean that there must be an issue of multicollinearity, but it just gives us the indication that these two variables are highly correlated. So we can dig deeper into these two variables to check out whether there is the issue of multicollinearity or not. So there is another test which normally we use, which is called VIF test, or variance inflation factor. And what it would do is it would give us some kind of a value for each independent variable. And if the VIF is above 10, then we would say that there is a multicollinearity issue with that variable. And you would normally see that, let's say x1 and x2, they both would have let's say value of 11, 11.5, then these two variables are multicollinear. They have a higher correlation. They are suffering from multicollinearity, and we might have to treat them. Some researchers suggest that this threshold should be kept at 5. So any value above 5 should be considered problematic. But again, that depends on the situation, and you can either use a conservative number or or the value of 10 as the cutoff rate. So a VIF of 10, what would it mean? It means that the variance of the coefficient is 10 times of that it should be if there was no multicollinearity. So that we saw that when there is multicollinearity, the variance would increase, right? The standard errors would increase. So the variance, how much would increase? If the value is 10, that would mean that the variance of that specific independent variable is 10 times that of it had been if there was no multicollinearity. So that is quite high of a variance. Just to give you an idea, how do we measure VIF? We do it by 1 divided by 1 minus the R square of that specific variable. So we run a regression between these two variables, and then we find out the R square. By the way, this aspect is called tolerance level. Okay, so once we have found that there is multicollinearity issue between our independent variables, then what should we do? What are the remedies that we can perform? The first is we should do nothing. And that is if the objective of our research is just the prediction and not drawing inference. Remember, it would still, the coefficient would be unbiased, the standard errors would increase. So if the standard errors would increase, the t value would decrease and the p value would increase. The confidence interval will be higher. So these are all the measures that we use for to draw inference. For hypothesis testing, we would not be able to draw inference, but our coefficient again would be unbiased. And we can leave this multicollinearity issue if there is the correlation is not higher. So we can do nothing in this case. One of the remedy is to just leave it as it is and just report the statistics. The second is to remove one of the correlated variables. So we saw that x1 and x2, they both were correlated. They had a correlation of 0.9 and the VIF turned out to be 11.5. So one of the remedies is either to remove x1 or x2 from the model. So if in case previously our model was alpha plus x1, beta 1 x1 plus beta 2 x2, then we might either drop this variable or this variable, and our model would simply become, let's just say, alpha plus beta 1 x1. Then in this case the multicollinearity would, the issue would be resolved. So this is the path that we choose if the variables are providing the same information. So normally we can remove the control variables. We have control variables in our model. But if the variable is of interest, then we cannot exclude it. If the variable is particularly important for that specific project, then it wouldn't make sense to remove that variable. Again, if you are dropping a variable, then you should specifically be aware of the omitted variable biasness. And what omitted variable biasness is, that we discussed in our previous video, that if you drop a variable that was important for that model. So if in case we are going to study the effect of income and wealth on consumption of a person, then the higher the income, the higher would be consumption, the higher the wealth, the higher would be the consumption. But these two variables have a problem, and that they are probably collinear, and that is because someone having a higher wealth would probably have a higher income, or someone having a higher income would probably have accumulated a higher wealth. So if we drop, so there is a correlation between this, that is understandable. So what remedy should we follow? If we are going to remove one variable, let's say we are going to remove wealth from this equation, but the issue is that consumption, the theory says that consumption is dependent on income and as well as the wealth. So if we drop wealth, then we are committing omitted variable bias, and then this effect would again turn out into error term, and that might generate another issue. Okay, so moving on, another remedy is to combine the correlated variables. So for example, in previous starting example, we saw the effect of experience and age on the teacher's salary. What we can do is, if these two variables, the number of years of experience and the age is correlated, then what we can do is we can somehow combine the information of these two variables and say we can construct a score, say seniority score, and now instead of having these two independent variables in the model, we can have just one independent variable, which would be seniority score. But that would accommodate both the information of the number of years of experience and the age. Okay, so we can change the measure, right? So if we have measured a variable in using some specific measurement, we can change that specific measurement. That might remove multicollinearity. And lastly, we can follow either principal component analysis. Principle of component analysis, what it does is, again, using certain technique, it combines the information of those variables. or we can increase the sample size. Remember, we discussed that multicollinearity also occurs because of a small sample size where there is limited variation. What we can do is we can increase the sample size, and that might remove multicollinearity.